Hi, Niels.
Yeah, hi.
Welcome to the podcast, Everyday Metallurgy, once again.
Yeah, thank you.
You
So I look forward to this. This will be fun. Yeah.
You were on the show about a year ago where you told about solidification and how that occurs. And I am reaching out to you now because I would like to learn more about how to use phase diagrams. And the specific reason for reaching out to you is that a couple of weeks ago on LinkedIn, I saw a post, and I'll just share my screen so you can see what I saw.
Mm-hmm.
I had this very beautiful microstructure from a particle made in manganese-nickel.
Yep.
It was shared by Martin Dopler from Metalpine and made together with Stefan Gnieger.
Mm-hmm.
And what you see are these very beautiful flowers. And when I looked at it, I think I can see maybe three phases: the white, the black, and the light gray. And then I would like to learn a bit more about what is it? What is going on? How does it solidify this way? Because it was also solidified with a very high speed. And then I looked at the phase diagram and I thought I might better reach out to Dr. Phase Diagram Niels Tiedje and ask for help.
Yeah.
So that's why you are on, Niels. Can you help me and the people who are watching this to understand what is going on with this solidification pattern?
I can at least try. Just for the record, because you said manganese nickel, it's magnesium nickel, right?
Sorry, yes, magnesium. Oh,
yeah,
yeah, you're right.
It could have a small influence on the result.
Absolutely. Yeah.
And yeah, thank you for inviting. It's a lovely picture, I think, and it's a very high magnification, as you can see if you see that the yardstick at the bottom is 10 microns. So these particles are, what are they, 50 microns across or something like that. And as you said, they are clearly very rapidly cooled. And therefore you also see all these flowers, or metallurgically they are called dendrites.
Yes.
Because they resemble trees, and you could imagine if you look at them, and if you take a pine tree and cut it a slice perpendicular to the growth of the tree, you could make a slice of the stem in the center and the branches coming out, and this is what we see here. And that's basically their tree-like structure. They look like trees. It's got nothing to do with trees, but they look like trees. And your question was what's going on here, but you were also referring to phase diagrams in general. And so we have to remember when we talk about phase diagrams, the phase diagrams is just, it shows what the world is like in a perfect state, when everything is at equilibrium, and you could say all the atoms are happy with where they're located. That is not often that it happens in real life. So phase diagram is sort of an intention of what should we expect to see in the world. And the phase diagram only shows us which phases may exist under certain conditions. It does not tell us that they will exist. It does not tell us what shape those phases will take. So the shape of those trees is actually quite a long discussion, but it is not directly related to the phase diagram. But the amount of phases is very much related to the phase diagram. So that's sort of just to start out with what we look at.
Yeah.
And
I'll just unsharing.
Yeah. So maybe I should share. I will come back to the same picture, and then I will show a phase diagram, and we can take it from there. Would that be okay? Yeah. So yes. I will just share, and we are. And we now see a phase diagram. And if we look at it, let me just get another pointer. Here we are. Yeah. What we see here is magnesium at this point. At the other end, we have nickel. So we're assuming at this point we have pure magnesium. At this point, we have magnesium with 10 mole percent nickel in it. Yeah. So we see X here is the mole fraction, which if you study thermodynamics is a classic way of looking at it. But if you're studying mechanical engineering, you would prefer weight percent. Yeah. But this is the thermodynamics approach. And if I just change to another picture, this is what it looks like when I have weight fraction. Okay. Or the weight percent. I should say also that these phase diagrams I have borrowed from a homepage that is listed down here, and it's calculated phase diagram, but it's nice and clean, so it's relatively easy to look at. Yeah. And thank you to the nice people who made it. We have here temperature in Celsius, and then we have the weight fraction. So this is 10 weight percent nickel, 20 weight percent nickel, and so on. Yeah. The alloy that we worked with is located 15%. Yeah. So it's located here. Yeah. At this point. And I was actually hoping that I could draw a little bit. Oh. Yeah, here. Sorry for the confusion. So we are here. Come on. This is not. Sorry about that. We are with the 15% here, located here. Yeah. And that means if I go up in temperature, and what the structure we saw is started somewhere at a high temperature. And then the phase diagram will show me at different points in temperature and mixture, what structures do we get. And if we look at magnesium, which is a hexagonal element, so pure magnesium would like to be hexagonal, we try to mix it with nickel, which is face-centered cubic. We can immediately see from the phase diagram that those two alloy elements do not mix very well. They really don't like each other, so to speak. Yeah. And we can see that in between pure magnesium and pure nickel, we have structures, phases that are stoichiometrical balanced. So we have magnesium, nickel 2, and we have magnesium 2, nickel. And this is hexagonal, and this is also hexagonal. We cannot see that from the phase diagram, but I know it because I read up on it yesterday. Yeah. So therefore we know that. And because that nickel, and we can actually see here, pure magnesium is one line, and in many other phase diagrams, there will be a gap somewhere here where we have magnesium with a little bit of nickel in it. Yeah, a little solubility. A little solubility, but there is hardly any solubility of nickel in magnesium. If we go to the other end, it is exactly the same. Magnesium does not dissolve in nickel. Yeah. So when they don't like each other, it's like oil and water. What do? If we want to mix them, then it turns out that if you substitute a certain number of magnesium elements with nickel, you can form this crystal structure, magnesium-2Ni, which is also hexagonal, but it just basically means that some of the points in the hexagonal lattice is substituted with nickel.
Yeah.
And therefore you can form a crystal, and that has, it is one structure that minimizes the free energy in the system, and phase diagrams come from the free energy. So this is something that can form. So if we are in this square field here, we can have two phases. We will have two phases, pure magnesium and this magnesium-2 nickel. They are both hexagonal, but they're different in composition. We are at this point. So below this line, we have a mixture of those two phases, and that's what we see on the picture. When we come from high temperature, the first thing that happens when the temperature is reduced is that we hit the solidus line for the magnesium. And that means at this point, we have a balance between pure magnesium and a liquid that contains 15% nickel.
Yeah.
In the nickel, or in the liquid, magnesium and nickel will mix quite nicely. So no problems here. But in the solid state, what happens when we lower the temperature? We get more magnesium. But the problem is the magnesium contains no nickel. So the nickel has to go somewhere. And therefore the nickel goes to the liquid. So the liquid concentration increases. And just before this eutectic temperature, we have a balance between pure magnesium and a liquid that contains 20-something weight% nickel. So we have a solid phase and a liquid phase with different chemical composition. And we can calculate with the lever rule, we can calculate the fraction of those two. I think we should come back to that if we have time, but just for the explanations, I think I will leave it at this point. So the first thing that forms is pure magnesium, and then later we have the nickel that comes out. When we hit this line, on that line, we can have a balance between three phases. We can have the magnesium, the Mg2Ni phase, and the liquid. And if we keep cooling, gradually all the liquid will turn into magnesium and Mg2Ni at the same time. So we have two phases with different composition that precipitates out of the liquid. When we're past that line, nothing more happens other than the material gets colder. But we have magnesium and nickel separate. And maybe if we had enough time to leave it, then we could imagine we had a block of magnesium, and then on top of that, or below that, maybe a block of magnesium to nickel. That would take millions of years. So that's not. Let's leave that scenario. And then maybe we should go to your picture, which I have here. And here I would like to see if I can make my pen work, because it's a little nicer to see if I can draw. So if we look at the dark areas here, because I already know about solidification and how structures form in solidification, I would say this dark matter that we see here is a dendrite that is formed from the first magnesium that comes when the first magnesium forms. So we should imagine a small tree growing in the liquid, and that liquid is, or that solid, the tree, is pure magnesium.
Mm-hmm.
And the liquid around the tree, as the tree grows, that liquid becomes more and more rich in nickel. And therefore, in the area we have out here around it, that is a liquid with high nickel content. When we get to the eutectic point, maybe if I am very good at this, I could make a small sketch.
Yeah.
And say we have magnesium, and then we have, I'm not going to draw the whole phase diagram, but let's just say we have nickel here, and we have this
The eutectic.
Mg2 nickel, and we have pure magnesium here. And as we may recall, our alloy is here with 15% nickel. So as the tree grows, the temperature, which is temperature here, the temperature is reduced, more and more tree is formed, the tree becomes bigger and bigger, and the liquid composition travels down this line. When we get to this point, below that line, everything solidifies. So at that point, we are extracting energy out of the system, and at that point, we have magnesium plus Mg2 Ni. This should have been magnesium, sorry about that. But it grows in the liquid. And therefore, I would have liked to have had a really nice close-up of this picture. I know the magnification is high enough as it is, so it's not easy. But I would expect, at least, to find little blobs of magnesium together with little blobs of nickel.
So it's a lamellar structure.
I don't know. I haven't checked it, but it is possible. It's very common
that it could be similar to perlite.
Exactly. Yeah. And perlite is a eutectoid transformation, which is a eutectic in solid state. So, but aluminium silicon has something similar. But let's just imagine if we have here magnesium. Then when we look at the phase, we look at the phase diagram, from that magnesium, we will have nickel atoms pushed into the liquid.
Yeah.
And that means next to it, we will have Mg2 nickel. And then we will have more magnesium. And that means that the nickel basically travels from one tip to the next while these materials grow, and it is very simple to exchange nickel atoms, to move nickel atoms from one to the other, and therefore those phases will grow at the same time next to each other. So in between the dendrites in this area, we will see these two phases growing at the same time, and of course we have liquid out here. And maybe at some point in the vicinity, we also have these magnesium dendrites. So in between the dendrites, we find this very fine phase forming in the material. That's what I would expect based on the phase diagram.
Yeah. It sounds very plausible. Then I have a question, because I remarked that the dendrites, the tree, had different colors. Is that only due to orientation then? Because if it's pure magnesium, all of it should look the same. But why are some of them dark and some of them are light gray?
Yeah. What we see here, this is backscatter electrons, as I remember, which means we have a contrast that is given by the elements that are in the material. So we have electrons shot onto the sample, and then we have electrons coming back into the system. And the energy of those electrons depends on what material they're reflected from, or they come out from. Yeah. And therefore we see a coloring. That's the reason for the color difference that we see.
Yeah.
And that basically means that in here we have more nickel than we have in the gray. But we also have to remember, I will draw on the other side. Come on. Sorry, it's very lively, this. But let's assume this is the surface of my sample. And I have an electron beam coming down here.
Yeah.
The electron beam analyzes a volume below the surface.
Penetrates. Yeah.
So if I have a dendrite arm here, I will, of course, see the dendrite arm, but I will also see the material below it.
Yeah.
If my dendrite arm is twice that thickness, I will get a slightly variation in color. And I do not know where I section these. I think that would be my main reason for seeing that difference in shade.
It's a pretty fair explanation.
And I think, it's 11. Hang on, that's wrong. I'm not sure what the acceleration voltage is. So I'm not going to say anything about that. So basically what we see are traces of these dendrites, and in between there should be a eutectic. The problem here is, of course, this is, I don't know how they're made, but they could be gas atomized particles. And therefore the cooling rate is extremely high.
Yeah.
And the microstructure is super fine. We have to imagine, if we look at this graph, to move a nickel atom from here to that point at a cooling rate of maybe 10,000 Kelvin per second, or you have to move fast. And therefore those structures really come close. Maybe we also see some supersaturation in the liquid. I just can't see it in what we have here. So we have to be a little bit careful with that. But if we slow down, like a classic sand casting process, you would definitely see some eutectic in there.
Fantastic.
Yeah, does that make sense?
Yes, I have learned something today.
Good.
Yeah. Niels, my idea was to take this up once in a while. So if people seeing this, they have a microstructure they would like to have analyzed, and they know the chemical composition, I would like to challenge you for new episodes, if you're willing to do that.
I'll give it a go. I can't promise to do everything correctly, and I can work with what I have. And again, in this case, we should really do an episode on solidification, why these structures look like they do, because you can do there could be some quite interesting things in these rapidly cooled structures. So, but anyway, with the information that I have, I would be happy to give it a go.
Thank you. I think I have got everything I need today. You made it extremely clear. So you can keep your new title, Dr. Solidification.
I'm happy with that. It's something I worked with a few years, and I find super interesting. So I'll be happy to assist.
Thank you very much.
Yeah.
Enjoy the day, Niels.
No worries. Yeah, you too.
Yeah.
Thanks very much. Bye.
Bye.